Welcome back to another Info Index video. Today we will be talking about the 0-1 knapsack problem of dynamic programming. Here's the problem outline. Given a knapsack of size S and n different items, each with a value of Vi and a weight of Wi, determine the maximum value you can get by placing some of these items into the knapsack. Here are some important rules. You only have one of each item. Once an item is placed in the knapsack, you cannot place it in the knapsack again. Items cannot be split. You either exclude an item from the knapsack or you include it, which is why it is called the 0-1 knapsack problem. Logically, the sum of the weights of the items in the knapsack must be less than or equal to the size of the knapsack. Here is the sample problem that we will be solving in this video. You have a knapsack of size 6. You have 4 different items. Item 1 has a value of 3 and a weight of 1. Item 2 has a value of 4 and a weight of 2. Item 3 has a value of 6 and a weight of 4. And item 4 has a value of 5 and a weight of 3. What is the maximum value you can obtain by placing a subset of these items into the knapsack? Here is the dynamic programming algorithm to solve this problem. First, define a two-dimensional array called dp. Let dpij represent the maximum value you can achieve using the first I items with a knapsack of size j. Since there are 4 items and the knapsack size is 6, I can be between 0 and 4 inclusive, and j can be between 0 and 6 inclusive. With this definition, the process of calculating the answer for any cell is dependent on the values of previously calculated results. The process for calculating the result for dpij is as follows. If I or j is equal to 0, then dpij is equal to 0. This is because if I is equal to 0, then you have access to the first 0 items, in which case you can't get any value. If j is equal to 0, then the size of the knapsack is equal to 0. Since all of the items have weights greater than 0, you can't place any items in the knapsack and therefore you can't get any value. Otherwise, if j, the size of the knapsack, is less than the weight of item I, then it is guaranteed that you can never use item I. So the answer will be the same as if you only had access to the first I-1 items. So if j is less than the weight of item I, dpij is the same as dpi-1j. Otherwise, there's a choice of whether item I is used or not. If item I is used in the knapsack, it cannot be used again, and then you only have access to the first I-1 items. Also, the knapsack space that remains will be j minus wi, where wi is the weight of item I. As you can see, dpi-1 j minus wi actually holds the maximum value you can obtain using your remaining items and remaining knapsack space. Simply add this to Vi, the value of item I, and you now have the maximum value you can get if item I is used. An expression for this is Vi plus dpi-1 j minus wi. Alternatively, you can choose not to use item I. If so, then you can eliminate item I from your available items, leaving you with access to the first I-1 items. The knapsack size has not changed. Therefore, the maximum value if item I is not chosen is represented by dpi-1j. Simply taking the larger value of these two expressions will give you the final result for dpij. To summarize, dpij is equal to 0 if I or j is equal to 0. If j is less than the weight of item I, it is equal to dpi-1j. Otherwise, dpij is equal to Vi plus dpi-1 j minus wi, or dpi-1j, whichever one is larger. Using the algorithm defined on the previous slide, we are now ready to fill in the table. If we are only allowed to access the first 0 items, or the knapsack size is 0, then the maximum achievable value is 0. Now we can start from dp11. Can a knapsack with size 1 hold item 1? Yes, because the weight of item 1 is 1. So, if item 1 is not chosen, then the maximum value is simply dp01. This is equal to 0. Otherwise, if item 1 is chosen, the maximum value is the value of item 1 plus the maximum value you can achieve using the remaining items and your remaining knapsack space. The value of item 1 is 3, and dp00 is 0. Adding them gives us 3. Since this is the larger value, dp11 is equal to 3. This logic can be repeated for the entire first row. Now we are at DP21. A knapsack with size 1 can never hold item 2, as the weight of item 2 is greater than the knapsack size of 1. Therefore, the maximum value will be the same as if you only had access to the first 1 items. This can be found in DP11. Now we are at DP22. The knapsack of size 2 can hold item 2 this time, so there is a choice of whether item 2 is used or not. If it is not used, then the maximum achievable value is DP12 or 3. If it is used, then the maximum achievable value is the value of item 2 plus DP10. This is equal to 4 plus 0 or 4. 4 is the larger value, so this is the answer. At DP23, the knapsack of size 3 can hold item 2, which means that item 2 can either be used or not used. Not using item 2 gives a maximum value of DP13, which is equal to 3. Using item 2 gives a maximum value of 4 plus DP11. This is equal to 4 plus 3, which is equal to 7. The larger value is 7, so this is the answer. If we repeat this logic, we can fill row 2. For DP31, DP32, and DP33, the knapsack size is less than the weight of item 3, which is 4. Therefore, the answer will be the cell directly above them. For DP34, not using item 3 results in a maximum value of DP24, or 7. Using item 3 results in a maximum value of 6 plus DP20, which is equal to 6 plus 0, which is equal to 6. 7 is the larger number, so the answer is 7. Using the same logic, we can complete row 3. By now, you should be clear on the algorithm for finding the answer to any cell. If not, feel free to go back to the dynamic programming algorithm slide for a full explanation. Using the same logic, row 4 can be completed, and the table looks like this. To answer the original question, what is the maximum value you can obtain by placing a subset of these items into the knapsack? The answer is stored in DP46. Therefore, the maximum value you can obtain is 12. Now, how do you get which items you have to use in order to achieve the maximum value of 12? First, start at the cell you wish to calculate the specific items used. At your current cell, let's call it DPIJ, check the cell above it, which is DPI-1j. If their values are equal, you did not use item I. Move over to the cell DPI-1j and repeat, using those values as the new values for I and j. If their values are not equal, then you used item I. Therefore, move over to the cell DPI-1j-wi and repeat, using those values as the new values for I and j. Remember that wi represents the weight of item I. Stop once you reach a cell where I equals 0 or j equals 0. This algorithm works for any cell, and we can use this to find the items used to achieve the maximum value of 12. Currently, we are at the cell DP46. The cell above it is not equal, so we used item 4. Move over to the cell DP33. Now we are at the cell DP33. The value above it is equal, so we should move to the cell DP23. For DP23, the cell above it is not equal, so we used item 2. Move over to the cell DP11. For DP11, the cell above it is not equal, so we used item 1. Move over to the cell DP00, and we should stop because I and j are both equal to 0. Finally, the items that were used were item 1, item 2, and item 4. We can verify that this is valid because the sum of the weights of item 1, 2, and 4 is 6, and the sum of their values is 12. Here is the summary. Solving the knapsack problem uses a bottom-up approach that stores the results of previous computations and uses them to solve larger and larger subproblems until you are able to get the final answer to the question. The process for calculating the maximum achievable value for the first I items in a knapsack of size j is intuitive. The time complexity of this algorithm is O(n) times s, where n is the number of items and s is the size of the knapsack. This was the Info Index lesson on the knapsack problem for dynamic programming. Be sure to leave a like and subscribe.